Welcome, cosmic adventurers. Take a moment to gaze up at the night sky. What do you see? Perhaps you're captivated by the twinkling stars scattered across the dark canvas above. Maybe you've spotted the reddish glow of Mars or the mesmerizing rings of Saturn. On a particularly clear night, you might even glimpse the faint smudge of the Andromeda Galaxy, a collection of billions of stars, some 2.5 million light-years away. Now imagine having the power to reach out and examine these celestial wonders up close, to peer into the heart of star-forming nebulae, or to witness the cosmic dance of colliding galaxies. This is precisely what telescopes allow us to do. Metaphorically speaking, of course. These remarkable instruments serve as humanity's windows to the cosmos, transforming those tiny points of light into breathtaking cosmic landscapes. Today, we're embarking on an extraordinary journey to explore two remarkable types of super eyes that humanity has created to unravel the mysteries of the universe, ground-based and space telescopes. From the snow-capped peaks of Mauna Kea in Hawaii to the very large telescope array in Chile's Atacama Desert, we'll discover how ground-based telescopes have revolutionized our understanding of the cosmos. Then we'll soar hundreds of miles above Earth's surface to explore the realm of space telescopes, like the legendary Hubble and its successor, the James Webb Space Telescope, which provide us with unprecedented views of the universe from their orbital perches. Our cosmic journey will take us through the challenges these instruments face, from Earth's turbulent atmosphere to the harsh environment of space. We'll explore how modern technology has transformed these challenges into opportunities, leading to groundbreaking discoveries that continue to reshape our understanding of the universe. From hunting distant exoplanets to studying the afterglow of the Big Bang, these technological marvels are pushing the boundaries of human knowledge further than ever before. So fasten your seatbelts and prepare for an adventure that spans from the highest mountain observatories to the most distant orbits around our planet. Together, we'll discover how these two different approaches to cosmic observation complement each other, working in harmony to unveil the secrets of our vast and mysterious universe. This is more than just a tale of two technologies. It's the story of humanity's endless quest to understand our place in the cosmos. Before we dive deeper into our cosmic exploration, let's take a fascinating journey through time to understand how telescopes evolved from simple tubes with lenses to the sophisticated machines that now unveil the universe's deepest mysteries. The story begins in the Netherlands, in the bustling town of Middelburg, where in 1608 an eyeglass maker named Hans Lippershey filed the first patent for a telescope. Legend has it that he discovered the principle when two children were playing with lenses in his shop, noticing that distant objects appeared closer when viewed through specific lens combinations. While Lippershey didn't receive his patent, his invention quickly spread across Europe, forever changing the course of human knowledge. But the real astronomical revolution came in 1609, when an Italian mathematician and scientist, Galileo Galilei, heard about this Dutch invention and decided to build his own version. Galileo's first telescope could magnify objects about 8 times, but he quickly improved his design to achieve 20 times magnification. When he pointed his instrument toward the night sky, he made observations that would shake the foundations of human understanding. He saw mountains and craters on the moon, discovered 4 moons orbiting Jupiter, observed the phases of Venus, and glimpsed countless stars never before seen by human eyes. The next major leap came in 1668, when Isaac Newton introduced the reflecting telescope, using mirrors instead of lenses to gather and focus light. This innovation solved the color distortion problems that plagued refracting telescopes and laid the groundwork for the massive telescopes we use today. Fast forward to the 19th century, and we witness the birth of truly giant telescopes. The 72-inch Leviathan of Parsonstown, built by the Earl of Ross in Ireland in 1845, allowed astronomers to observe spiral structures in galaxies for the first time. The dawn of the 20th century brought even larger instruments, like the 100-inch Hooker telescope at Mount Wilson Observatory, which Edwin Hubble used to prove that the universe extends far beyond our Milky Way. But perhaps the most revolutionary step in telescope evolution came in 1990, with the launch of the Hubble Space Telescope. For the first time, we had an observatory free from Earth's atmospheric interference, capable of capturing the cosmos with unprecedented clarity. This marked the beginning of the space telescope era, leading to a new generation of orbital observatories that study the universe across the entire electromagnetic spectrum. Today, we stand at the threshold of an exciting new chapter in telescope history. Ground-based telescopes have grown to enormous proportions, with mirrors spanning tens of meters, while space telescopes like the James Webb push the boundaries of what's possible in space-based observation. Each new generation of telescopes builds upon the innovations of the past, allowing us to peer further into the cosmic ocean and uncover more of its secrets. Before we continue our journey through the cosmos, take a moment to join our community of space enthusiasts. Hit that like button, share this video with fellow cosmic explorers, and subscribe to Exploring the Universe to ensure you don't miss any of our fascinating space adventures. Now let's venture further into the world of modern telescopes. Let's delve into the fascinating world of ground-based telescopes, the veterans of celestial observation that have been our primary windows to the cosmos for over 4 centuries. Ground-based telescopes are remarkable feats of engineering that come in various designs and sizes, each with its own specialized purpose. Let's break down the 2 main types that have shaped our understanding of the universe. First, we have refracting telescopes, the oldest telescope design. These instruments use a system of lenses to gather and focus light, similar to how a magnifying glass works, but on a much grander scale. The front lens, called the objective lens, collects light from distant objects and focuses it to create a clear image. While refracting telescopes provide excellent contrast and are fantastic for observing planets and the moon, they face a practical limitation. The larger the lens becomes, the heavier and more expensive it is to manufacture. The largest practical refracting telescope ever built, the Yerkes Observatory's 40-inch telescope, completed in 1897, remains the largest of its kind. But the real giants of modern astronomy are reflecting telescopes. Instead of lenses, these instruments use enormous mirrors to collect and focus light. The primary mirror sits at the bottom of the telescope tube like a giant light bucket, gathering photons from distant cosmic objects and reflecting them to a focus point where they can be analyzed. The beauty of reflecting telescopes is that mirrors can be made much larger than lenses and can be supported from behind, allowing for truly massive instruments. And when we say massive, we mean it. The current generation of ground-based telescopes features primary mirrors that would make your jaw drop. The twin Keck telescopes in Hawaii each have mirrors 10 meters, 33 feet across, composed of multiple hexagonal segments working together as a single reflecting surface. The Gran Telescopio Canarias in Spain boasts a mirror 10.4 meters wide, and the very large telescope in Chile consists of 4 2-meter telescopes that can work together to achieve the light-gathering power of a much larger instrument. These modern behemoths are housed in sophisticated domes atop some of Earth's highest and driest locations. Places like Chile's Atacama Desert, Hawaii's Mauna Kea, and the Canary Islands provide ideal conditions: clear skies, minimal atmospheric turbulence, and low humidity. Each telescope dome is a technological marvel in itself, using advanced systems to maintain optimal temperature and protect the delicate instruments within. But what makes these ground-based telescopes truly remarkable is their advanced technology. Many now employ adaptive optics systems that use deformable mirrors controlled by powerful computers to compensate for atmospheric distortion in real time. Imagine a mirror that can change its shape 1,000 times per second to counter the twinkling of stars, resulting in images nearly as sharp as those taken from space. The light-gathering power of these instruments is staggering. To put it in perspective, the largest ground-based telescopes can collect enough light to see a single candle flame on the moon. They can peer so deep into space that they can observe galaxies as they appeared billions of years ago, effectively looking back in time to when the universe was young. These terrestrial giants serve as our primary workhorses in astronomy, conducting long-term surveys of the sky, studying the motion of stars and galaxies, and helping us understand the fundamental physics that governs our universe. They work tirelessly night after night, gathering the photons that tell us stories of cosmic creation, stellar evolution, and the dance of galaxies across the vastness of space. Looking ahead, even larger ground-based telescopes are under construction. The extremely large telescope in Chile will feature a primary mirror 39.3 meters in diameter, nearly half the length of a football field. These next-generation instruments will push the boundaries of what's possible in astronomical observation, promising to reveal even more secrets of our cosmic neighborhood. Now, let's venture beyond Earth's atmosphere to explore the remarkable world of space telescopes, humanity's eyes in orbit. These extraordinary instruments, floating hundreds or thousands of miles above our planet's surface, represent one of our greatest technological achievements in the quest to understand the cosmos. Space telescopes are essentially sophisticated observatories launched into space, designed to capture the universe's light free from atmospheric interference. Unlike their ground-based counterparts, these orbital observatories provide us with crystal-clear views of cosmic phenomena, operating in the pristine vacuum of space where there's no atmospheric turbulence to distort their vision. The most famous of these cosmic sentinels is undoubtedly the Hubble Space Telescope, launched in 1990. Orbiting approximately 340 miles above Earth's surface, Hubble has revolutionized our understanding of the universe. This bus-sized observatory has captured breathtaking images of stellar nurseries, dying stars, colliding galaxies, and countless other cosmic wonders. Its contributions to astronomy are immeasurable, from helping determine the age of the universe to providing evidence for the existence of dark energy. But Hubble isn't alone in its cosmic watch. A fleet of space telescopes now orbits our planet, each designed to observe different parts of the electromagnetic spectrum. The Chandra X-ray Observatory peers into the high-energy universe, revealing the violent physics around black holes and supernovae. The Spitzer Space Telescope, before its retirement in 2020, studied the infrared universe, penetrating cosmic dust clouds to reveal hidden star formation and planetary systems. The newest member of this space-based family is the James Webb Space Telescope, launched in 2021. Positioned about 1 million miles from Earth at the L2 Lagrange point, Webb represents the most powerful and complex space telescope ever built. Its massive 6.5-meter golden mirror, protected by a tennis court-sized sun shield, allows it to observe some of the earliest galaxies that formed in our universe, peer through cosmic dust clouds, and study the atmospheres of distant exoplanets. Space telescopes offer unique advantages that make them invaluable for astronomical research. Operating above Earth's atmosphere, they can detect wavelengths of light that never reach our planet's surface, such as much of the infrared, ultraviolet, and X-ray spectrum. This capability allows them to observe phenomena invisible to ground-based telescopes, providing crucial data about the physical processes shaping our universe. These orbital observatories also benefit from the stable environment of space. Without atmospheric interference, they can maintain their focus on distant objects for extended periods, sometimes for hundreds of hours, allowing them to collect light from some of the faintest and most distant objects in the cosmos. This stability also enables them to achieve unprecedented image clarity, revealing fine details that would be impossible to see from Earth. However, operating telescopes in space presents unique challenges. Once launched, they must function perfectly in the harsh environment of space, enduring extreme temperature variations, radiation, and micrometeoroid impacts. Unlike ground-based telescopes, repairs or upgrades are extremely difficult and costly, as demonstrated by the famous Hubble repair missions that required space shuttle crews to visit the telescope in orbit. The future of space telescopes looks even more promising. Plans are underway for next-generation observatories that will search for signs of life on exoplanets, study the nature of dark matter and dark energy, and push our observational capabilities to new limits. These future missions may include telescopes with even larger mirrors, perhaps assembled in space, or networks of smaller telescopes working together as virtual giant telescopes. Space telescopes represent humanity's ultimate vantage point for observing the cosmos. They are our silent sentinels in space, tirelessly gathering the light from distant worlds and helping us unravel the deepest mysteries of our universe. Every image they capture, every bit of data they collect, adds another piece to the grand puzzle of cosmic understanding that humanity has been assembling since we first looked up at the stars with wondering eyes. Let's dive into the fascinating world of telescope differences, where the battle between Earth and space creates a remarkable story of astronomical observation. The key distinctions between these two types of telescopes primarily stem from their operating environments, each presenting unique challenges and opportunities. The most fundamental difference lies in how these telescopes interact with Earth's atmosphere. Ground-based telescopes must peer through what amounts to a turbulent ocean of air. This atmospheric interference creates several challenges. Imagine trying to read a book through a flowing stream of water. That's similar to what ground-based telescopes face every night. The atmosphere distorts incoming light through a process astronomers call seeing, which causes stars to twinkle. While romantic for stargazers, this twinkling is actually a significant problem for astronomical observations. Modern ground-based telescopes have developed ingenious solutions to combat atmospheric interference. Adaptive optic systems use deformable mirrors that change shape hundreds of times per second, counteracting atmospheric distortion in real time. These systems often employ powerful lasers to create artificial guide stars in the upper atmosphere, helping telescopes calibrate their adaptive optic systems. It's like having a pair of prescription glasses that constantly adjusts to give you the clearest possible vision. Space telescopes, floating far above our atmosphere, don't face these challenges. They have crystal-clear views of the cosmos, unimpeded by atmospheric interference. This placement allows them to detect forms of light that never reach Earth's surface. Ultraviolet rays, X-rays and gamma rays, which are mostly blocked by our atmosphere, can be readily observed by space-based instruments. This capability has opened entirely new windows for studying high-energy phenomena like black holes, neutron stars, and supernovae. However, the story isn't as simple as space telescopes are better. Ground-based telescopes hold several significant advantages. First, there's the matter of size. Ground-based telescopes can be built on an enormous scale because they don't need to be launched into space. The largest ground-based telescopes have mirrors spanning dozens of meters, while space telescopes are limited by rocket payload capabilities. The James Webb Space Telescope's 6.5-meter mirror, while impressive for a space telescope, is dwarfed by ground-based giants. Maintenance and upgrades represent another crucial difference. Ground-based telescopes can be easily accessed for repairs, updates, and equipment modifications. If a component fails or new technology becomes available, astronomers can simply replace or upgrade the necessary parts. Space telescopes, once launched, are extremely difficult and expensive to service. The Hubble Space Telescope's repair missions, while successful, required complex space shuttle operations costing billions of dollars. Cost is indeed a major differentiator. Building and operating a ground-based telescope, while expensive, is typically far less costly than launching and maintaining a space telescope. This economic factor allows for more ground-based telescopes to be built, creating a wider network of observatories that can work together on various astronomical projects. There's also the matter of observation time and flexibility. Ground-based telescopes can operate every clear night, providing extensive observation time for numerous research projects. While they're limited by weather conditions and daylight, their greater numbers and lower operational costs make them more accessible to the astronomical community. Space telescopes, while able to observe 24/7 without weather concerns, are in extremely high demand, with observation time carefully rationed among competing research proposals. Another interesting difference lies in their respective roles in astronomical research. Ground-based telescopes excel at large-scale sky surveys, monitoring near-Earth objects and conducting long-term observations of brighter objects. Space telescopes are often reserved for observing the faintest and most distant objects, or for observations requiring their unique capabilities, such as ultraviolet or X-ray detection. The future of astronomy lies not in choosing between these two types of telescopes, but in their complementary use. Many modern astronomical discoveries rely on coordinated observations from both ground and space-based instruments, each contributing its unique strengths to create a more complete picture of our universe. This synergy between Earth and space-based observation represents the pinnacle of modern astronomical research, allowing us to probe deeper into the cosmos than ever before. And speaking of exploration, if you're enjoying this cosmic journey through the world of telescopes, don't forget to show your support by hitting that like button. I'm curious, if you could design your own telescope, would you build it on Earth or launch it into space? Share your thoughts in the comments below. Your perspective adds to our collective understanding of these amazing instruments. Let's explore how both types of telescopes are actually used in modern astronomy, revealing their practical roles in uncovering the universe's secrets. Each type of telescope serves specific purposes, contributing uniquely to our understanding of the cosmos. Ground-based telescopes excel in several key areas of astronomical research. Their large light-collecting surfaces make them particularly effective for studying bright, relatively nearby objects. When observing planets in our solar system, these telescopes can track changes in Mars' atmosphere, study Jupiter's dynamic storm systems, and monitor Saturn's rings with remarkable detail. The ability to upgrade their instruments regularly means they can incorporate the latest technology for planetary observation. These terrestrial observers play a crucial role in planetary defense. Their wide fields of view enable them to conduct comprehensive sky surveys, scanning large portions of the night sky to detect and track near-Earth objects, NEOs. Networks of ground-based telescopes work together in monitoring potentially hazardous asteroids, providing early warning systems for Earth's safety. The Pan-STARRS telescopes in Hawaii, for example, have discovered thousands of asteroids and comets, significantly contributing to our catalogue of solar system objects. Ground-based telescopes are also vital for studying stellar physics. Their ability to conduct long-term observations makes them perfect for monitoring variable stars, detecting stellar flares, and studying binary star systems. The large mirrors of modern ground telescopes can collect enough light to study star clusters in nearby galaxies, helping us understand stellar evolution in different environments. Space telescopes, on the other hand, demonstrate their unique capabilities in several specialized areas. The Hubble Space Telescope has been revolutionary in observing extremely distant galaxies, providing glimpses of the universe as it appeared billions of years ago. Its clear view, unobstructed by Earth's atmosphere, allows it to detect faint objects that would be impossible to see from the ground. In the field of exoplanet research, space telescopes like Kepler and TESS have been game changers. Their stable viewing platform allows them to detect the tiny dips in starlight caused by planets passing in front of their host stars. The James Webb Space Telescope takes this further, capable of analyzing the chemical composition of exoplanet atmospheres, searching for potential biosignatures that might indicate the presence of life. Space telescopes are crucial for studying phenomena at different wavelengths. X-ray telescopes like Chandra observe the hot, violent universe, revealing the physics of black holes, neutron stars, and supernovae remnants. Infrared telescopes can peer through cosmic dust clouds, showing us regions where new stars and planets are forming. Gamma-ray telescopes detect the most energetic events in the universe, from gamma-ray bursts to active galactic nuclei. Both types of telescopes work together in studying large-scale cosmic structures. Ground-based telescopes conduct extensive galaxy surveys, mapping the distribution of matter across vast regions of space. Space telescopes then provide detailed views of specific galaxies and clusters, helping us understand galaxy evolution and the effects of dark matter and dark energy. In cosmology, this partnership is particularly valuable. Ground-based telescopes map the large-scale structure of the universe, while space telescopes like Hubble and Webb provide deep-field observations that reveal how galaxies formed and evolved over cosmic time. Together, they help us piece together the universe's history, from the first galaxies to the complex structures we see today. Modern astronomical research often combines data from both types of telescopes to achieve comprehensive results. For instance, when studying a supernova, ground-based telescopes might discover and monitor the initial explosion, while space telescopes provide detailed spectroscopic data about the explosion's chemistry and physics. This complementary approach has become standard practice in astronomy, maximizing the strengths of each type of observatory. Looking to the future, these practical applications continue to evolve. New ground-based telescopes with mirrors 30 meters or larger will push the boundaries of what we can observe from Earth. Meanwhile, next-generation space telescopes will be designed to search for biosignatures on exoplanets and study the nature of dark matter and dark energy. Together, they will continue to expand our understanding of the cosmos, each contributing its unique capabilities to the grand endeavor of astronomical discovery. To delve deeper into this fascinating subject, let's turn to leading experts in the field of astronomy who work with both ground-based and space telescopes. Dr. Jane Rigby, NASA's project scientist for the James Webb Space Telescope, offers valuable insights into the complementary nature of these observatories. According to Dr. Rigby, both ground-based and space telescopes are absolutely essential for advancing our understanding of the universe. Ground-based telescopes are becoming increasingly powerful, with adaptive technologies that correct atmospheric distortion in real time. Space telescopes, on the other hand, give us access to types of light that never reach Earth's surface. The future of astronomy lies in the synergy between these two types of observatories. This perspective is echoed by Dr. Heidi Hamel, Vice President of the Association of Universities for Research in Astronomy, who emphasizes that modern astronomical discoveries often rely on coordinated observations from both types of telescopes. She explains that ground-based telescopes excel at large-scale sky surveys and long-term monitoring programs, while space telescopes are crucial for detailed observations of distant and faint objects. Dr. Andrea Ghez, who won the Nobel Prize in Physics for her work using ground-based telescopes to study the supermassive black hole at the center of our galaxy, points out that the combination of ground and space-based observations has revolutionized our understanding of the universe. She notes that the adaptive optic systems on ground-based telescopes can now achieve resolution comparable to space telescopes, while their larger collecting areas allow them to gather more light from faint objects. Dr. John Mather, Nobel laureate and senior project scientist for the James Webb Space Telescope, adds that the relationship between ground and space telescopes is not competitive, but collaborative. He explains how ground-based telescopes often identify interesting targets for detailed follow-up observations by space telescopes, while space telescope discoveries frequently require additional monitoring and analysis from ground-based facilities. Professor Brian Schmidt, another Nobel laureate in physics, emphasizes that the future of astronomy depends on maintaining and advancing both types of observatories. He points out that major discoveries, such as the acceleration of the universe's expansion and the detection of gravitational waves, require data from both ground and space-based instruments working in concert. The consensus among these experts is clear. The future of astronomy lies not in choosing between ground-based and space telescopes, but in leveraging the strengths of both. Each type of telescope brings unique capabilities to the table, and when their data is combined, we obtain a more complete and detailed picture of our universe. This collaborative approach has already led to numerous breakthrough discoveries and will continue to push the boundaries of our cosmic understanding. As we move forward, these experts anticipate even greater cooperation between ground and space observatories. Future discoveries about dark matter, dark energy, exoplanets, and the early universe will likely emerge from the combined efforts of both types of telescopes, each contributing its unique perspective to our grand cosmic exploration. Let's explore some mind-blowing facts about telescopes that will leave you in awe of these remarkable cosmic explorers. These fascinating tidbits showcase just how far we've come in our quest to understand the universe. Did you know that the largest ground-based telescope currently under construction, the extremely large telescope in Chile, will have a primary mirror nearly 40 meters in diameter? To put this in perspective, that's almost half the length of a football field. The mirror will be so large that it must be constructed from 798 hexagonal segments working together as one massive light-gathering surface. When completed, it will collect more light than all of today's largest telescopes combined. Speaking of impressive engineering, the James Webb Space Telescope sunshield spans the size of a tennis court, yet is thinner than a human hair. Its primary mirror, composed of 18 gold-plated beryllium segments, unfolds in space like a cosmic flower blooming in the darkness. At 5 meters in diameter, it's more than 3 times larger than Hubble's mirror, yet when folded, it fit inside a rocket about the size of a school bus. Here's a fascinating fact that few people know. The largest single-piece mirror ever made for a telescope belongs to the Large Binocular Telescope in Arizona. Each of its 2 primary mirrors measures 8.4 meters across and took nearly 7 years to cast and polish. The mirror was created by spinning molten glass in a rotating furnace, allowing gravity to naturally form its curved shape. The Hubble Space Telescope, despite being smaller than many modern ground-based telescopes, has made over 1.5 million observations and generated more than 19,000 peer-reviewed scientific papers. It's traveled more than 4 billion miles in orbit around Earth, or roughly the distance to Neptune and back. Ever wondered about telescope temperatures? The very large telescope in Chile's mirrors are kept at precisely the same temperature as the predicted night air to prevent any thermal distortion. Meanwhile, the James Webb Space Telescope operates at a frigid 233 degrees Celsius and must be kept cold enough to see the faint infrared light from distant galaxies. Here's a surprising fact about adaptive optics. Modern ground-based telescopes use powerful lasers to create artificial stars in the sky. These laser guide stars help telescopes measure and correct for atmospheric distortion thousands of times per second, producing images nearly as sharp as those taken from space. The radio telescopes offer their own set of incredible facts. The Event Horizon Telescope, which captured the first ever image of a black hole, isn't a single telescope at all. It's a network of radio telescopes spanning the entire globe, working together to create a virtual telescope the size of Earth itself. Some telescopes can detect light so faint that it would be equivalent to seeing a candle flame on the moon from Earth. The Large Synoptic Survey Telescope, now known as the Vera-C, Rubin Observatory, will photograph the entire available sky every few nights, producing about 20 terabytes of data per night, enough to fill about 20 million books. Perhaps one of the most remarkable facts is about the speed of astronomical observations. While light from the moon takes about 1.3 seconds to reach Earth-based telescopes, the James Webb Space Telescope observes objects so distant that their light has been traveling for over 13 billion years. When we look through Webb, we're literally seeing the universe as it appeared shortly after the Big Bang. And here's a final fascinating detail. If you were to count every star that the Hubble Space Telescope can see in a portion of sky the size of a grain of sand held at arm's length, you would count around 10,000 galaxies, not stars, but entire galaxies, each containing billions of stars. These incredible facts remind us that telescopes are more than just scientific instruments. They're time machines, light collectors, and windows into the deepest mysteries of our cosmos. They represent humanity's endless curiosity and our remarkable ability to build tools that extend our vision far beyond our earthly limitations. As we venture deeper into the 21st century, both ground-based and space telescopes face unique challenges, while promising extraordinary possibilities for the future of astronomy. Let's explore these challenges and the exciting prospects that lie ahead. Ground-based telescopes confront several pressing issues. Light pollution stands as one of the most significant challenges, with expanding urban areas creating an ever-brightening sky that interferes with astronomical observations. Major observatories worldwide are actively working with local governments to implement dark sky policies, but the problem continues to grow. Some observatories have even developed sophisticated software algorithms to help subtract artificial light from their observations. Climate change presents another formidable challenge for ground-based astronomy. Rising global temperatures affect atmospheric stability, potentially degrading observing conditions at traditionally excellent sites. Changes in weather patterns can lead to more frequent extreme weather events, increased cloud cover, and altered atmospheric conditions that impact telescope operations. Some observatories report fewer clear nights per year than in previous decades, directly affecting their scientific output. Space telescopes face their own set of challenges. The astronomical cost of space missions remains a significant barrier, with price tags often running into billions of dollars. The James Webb Space Telescope, for instance, cost approximately $10 billion to develop, build, and launch. These high costs limit how many space telescopes we can deploy and maintain simultaneously. The technical complexity of space telescopes presents another major challenge. Unlike ground-based telescopes, they must work perfectly from the moment they're deployed, as repairs in space are extremely difficult and costly. The harsh environment of space, with its extreme temperatures, radiation, and micrometeoroid impacts, requires incredibly robust engineering solutions. However, the future of telescope technology looks remarkably promising. For ground-based telescopes, we're entering an era of extremely large telescopes. The Giant Magellan Telescope, the 30-meter telescope, and the European Extremely Large Telescope are all under construction, promising to revolutionize our view of the cosmos. These behemoths will use advanced adaptive optic systems that can correct for atmospheric distortion better than ever before. potentially achieving resolution superior to current space telescopes. The next generation of space telescopes holds equally exciting prospects. NASA is developing concepts for telescopes that could directly image Earth-like exoplanets around nearby stars, potentially detecting biosignatures that could indicate the presence of life. The proposed large UV optical IR surveyor could be over 4 times larger than the James Webb Space Telescope, with unprecedented capabilities for studying everything from exoplanet atmospheres to the formation of the first galaxies. We're also seeing innovative new approaches to telescope design. Scientists are exploring the possibility of liquid mirror telescopes on the Moon, taking advantage of the lunar environment to create massive telescopes at a fraction of the cost of conventional designs. Others are developing swarms of small satellites that work together as a single virtual telescope, potentially achieving the light-gathering power of much larger instruments. Quantum technology might also revolutionize telescope capabilities. Quantum sensors could potentially detect individual photons with unprecedented precision, while quantum computing could help process the enormous amounts of data generated by modern telescopes more efficiently. Perhaps most excitingly, we're seeing increased international collaboration in astronomy. Future telescopes, both ground-based and space-based, are increasingly being planned as global endeavors, sharing costs and expertise across nations. This collaborative approach not only makes more ambitious projects possible, but also ensures that the benefits of these amazing instruments are shared globally. The challenges we face are significant, but they're driving innovation in telescope design and operation. As we develop solutions to these challenges, we're not just solving problems, we're creating new capabilities that will allow us to explore the cosmos in ways we never thought possible. The next few decades promise to be a golden age for astronomical discovery, with new telescopes revealing previously invisible aspects of our universe, and potentially answering some of humanity's most profound questions about our place in the cosmos. As we draw our cosmic journey to a close, let's reflect on the remarkable story of humanity's windows to the universe. Throughout our exploration today, we've discovered how ground-based and space telescopes work together as humanity's supreme tools for unraveling the mysteries of the cosmos. Ground-based telescopes, our terrestrial giants, stand as testaments to human engineering and innovation. These massive instruments, with their enormous light-gathering power, serve as our primary workhorses in astronomical research. From their mountaintop perches in some of Earth's most remote locations, they scan the heavens night after night, collecting the ancient light from distant stars and galaxies. Despite the challenges posed by our atmosphere, modern technology has transformed these instruments into incredibly powerful tools, capable of piercing the cosmic veil with remarkable clarity. Space telescopes, our orbital sentinels, represent a different but equally crucial approach to astronomical observation. Free from atmospheric interference, these sophisticated instruments provide us with pristine views of the cosmos. They can detect forms of light, from X-rays to infrared radiation, that never reach Earth's surface, revealing phenomena invisible to ground-based telescopes. The Hubble Space Telescope alone has revolutionized our understanding of the universe, while newer instruments like the James Webb Space Telescope promise to push the boundaries of our cosmic knowledge even further. The synergy between these two types of telescopes has proven to be one of astronomy's greatest strengths. Ground-based telescopes excel at large-scale surveys and long-term monitoring projects, while space telescopes provide unparalleled detail and access to different parts of the electromagnetic spectrum. Together, they form a comprehensive network of cosmic observers, each contributing its unique capabilities to our understanding of the universe. This partnership has led to some of astronomy's most significant discoveries, from the detection of thousands of exoplanets to the observation of gravitational waves, from mapping the large-scale structure of the universe to studying the birth and death of stars. These complementary approaches have dramatically expanded our cosmic perspective. They've shown us that we live in an expanding universe filled with billions of galaxies, each containing billions of stars, and that our cosmic story is far more rich and complex than we ever imagined. Looking ahead, the future of astronomical observation appears brighter than ever. New generations of both ground-based and space telescopes are being developed, each more powerful than its predecessors. These future instruments promise to reveal previously invisible aspects of our universe, from the atmospheres of Earth-like planets orbiting distant stars to the very first galaxies that formed after the Big Bang. Perhaps most importantly, our telescopes have transformed our understanding of our place in the cosmos. They've shown us that we are part of a vast, dynamic universe that stretches far beyond our imagination. Yet rather than diminishing our significance, these discoveries have highlighted the incredible privilege we have as conscious beings capable of comprehending and studying this magnificent cosmic dance. As we conclude our journey through the world of telescopes, we're reminded that every technological advance, every new discovery, brings us closer to answering some of humanity's most profound questions. How did our universe begin? How did galaxies, stars, and planets form? Are we alone in the cosmos? The partnership between ground-based and space telescopes continues to be crucial in our quest for these answers, serving as our steadfast guides in humanity's greatest adventure, the exploration of the final frontier. In the end, telescopes are more than just scientific instruments. They are the embodiment of human curiosity and ingenuity, our bridges to the cosmic unknown. As we continue to push the boundaries of what's possible, both on the ground and in space, we can look forward to even more remarkable discoveries that will reshape our understanding of the universe and our place within it.